Good morning, everyone. Can you hear me?
Good morning, sir. We can hear you.
Thank you. Thank you very much. I want to project the whiteboard, so please tell me if you can see it.
Yeah, we can see it.
Thank you. Thank you very much. Last week, we managed to drive a number of things. We managed to drive a number of things. I wanted to talk about the Friday tutorial, but I don't have the energy yet. So maybe as we progress, we'll talk about some of the things that happened on Friday. So let's just for now deal with what is in the notes. So I will take you back first. We have the model there, yi, which is equal to beta 0 plus beta 1 xi plus the random error term. So you know that our model is a sum of two components, which is the constant term and the error term. And the constant term is beta 0 plus beta 1 xi, and the error term is epsilon I. And we know that the error term is normally distributed with a mean of 0 and a constant variance sigma squared. So we have discussed that. So the random error term is normally distributed with a mean of 0 and a constant variance sigma squared. And because of that, the response variable, which is y in this case, the response variable, I think people should start paying attention to this, because I said I will talk about this later, but let me just do it. People are saying in the tutorials, I ask questions differently. And it's not correct, because if you pay attention, you will get these things. Now, I say find the variance of the response variable. You have to know what is a response variable, because tomorrow I might say find the variance of the dependent variable. You must know what is a dependent variable. So I cannot always say find the variance of y, find the variance of beta 1. What is beta 1? You must be able to know what is beta 1, what is the response variable, like that. Because we discuss these things here every day. So the expected value of the response variable. And by the way, as I've said, if we are dealing with a problem, then the response variable, like we did, it was the max. So I'll say find the variance of the max. So you must be able to know that the max is the the response variable. So you must be able to know all these things. So the expected value of the response variable, which is the expected value of y, it's equal to the constant of the model. And the constant term of the model is beta 0 plus beta 1 xi. And the variance of y, it's equal to the variance of the error term, because the variance of the constant term, it's equal to 0. So we are left with the variance of the error term, because from this, when we want the expected value of the constant is a constant, and the expected value of the error term is going to be 0, because we know that the error term is normally distributed with the mean of 0. But for the variance, when you take the var of this and the var of the error term, the var of the constant term is equal to 0, and we are left with the var of the error term, and that is sigma squared. And because y is a linear function of a normally distributed random variable, which is the error term, so y, which is the response variable, also follows a normal distribution. So it is following a normal distribution because it's a linear function of a normally distributed random variable. So you must get that one right. So here we are dealing with a population. So this is the true model. This is the true model. So this is the population model. But you know the reasons why we always opt for a sample rather than a population. So the same thing happens here. Instead of dealing with the entire sample, with the entire population, we go to the population and take a sample that will best represent the population. So from here, now we have yi hat, which is equal to beta 0 hat plus beta 1 hat xi, which is the estimated model, So we are estimating the population using the sample.
Sir, is it not x bar?
It's yi hat, which is equal to beta 0 hat plus beta 1 hat xi. We are moving from this. We are just from this. We are from here. So we are estimating the parameters, and that's what we are having. So the xi is still like that. It's xi. So we have the estimated model. We discussed the method of estimation. So we estimated these betas using the least square. And there's also the maximum likelihood. So we're going to start with the maximum likelihood today because we did not get time to discuss it last week. So you know how to estimate these betas using the least square. Then you also know, because we also showed that these estimators are unbiased. We also showed that these estimators are unbiased. So you also know that we did this. These estimators are unbiased, and we also derived the variances of these estimators. We also derived the variances of these estimators. So you also know the variances of these estimators. We also standardized this. We can also standardize beta 1 hat, which is equal to beta 1 divided by the standard deviation, the square root of the variance of beta 1. So we can also standardize. This follows normal with mean 0 and a unit variance. And we said because we have sigma there, which is unknown as well, we have to estimate it using S. And after estimating that, then this tend to follow a student T distribution. So you know those things. So I was just taking you back so that you can follow where we are going. So today we are going to discuss the maximum likelihood. We're going to estimate the parameters using the MLE. So it's start here. Oh, sorry about that. Let me do it like this. So we have the maximum likelihood estimation. So the maximum likelihood estimate of the sample can be developed if we assume that the response variable has a normal distribution. So we know that the response variable yi has a normal distribution because the errors are normally distributed. So we want to use we have to use the normal distribution that we discussed last year with Mr. Maj. So we have to use that normal distribution function, which is given by 1 over the square root of 2 pi sigma squared e to the power negative 1 over 2 sigma squared yi minus the mean, which is mu. And the mu is the population mean. And when I started now, I presented yi and also gave you the, or showed you the mean of yi, which is the population mean. So the population mean in this context is beta 0 plus beta 1 xi. So that is the population mean. So where there's mu in the normal distribution function, we replace by beta 0 plus beta 1 xi, and we end up with this function. So we end up with this function. So this is the normal function that you know. We replaced from mu there by the mean, because mu is the population mean, and the population mean here, it's beta 0 plus beta 1 xi. And because there is a negative here, that's why the beta 1 now it's having a negative sign. Is that one clear?
Yes.
Yes,
Thank you
yes,
very much.
Come
Thank you
again,
very
sir.
much. So, all right, let me do this. Let me go to the whiteboard and we deal with this from that side. Can you see the whiteboard?
Yes.
Thank
Yes,
you
we
very
can
much.
see it.
Thank you. So our function, which is f of y, it's 1 over the square root of 2 pi sigma squared e to the power 1 over 2 sigma squared yi minus the mean, which is mu. And this mu is the mean of, is the population mean of these observations, the yi's. So in this case, our yi, it's beta 0 plus beta 1 xi plus ei. And the mean of that, which is equal to the expected value of y, it's equal to beta 0. Sorry, this is beta 1 plus beta 1 xi. So this is our mean. And we take this mean and substitute it where there's mu. So our function now becomes f of y, which is equal to, let me write this like this. I want to get rid of that fraction there, to the power minus 1 over 2. E to the power 1 over 2 sigma squared yi minus, so now I'm taking the mean in there. So it will be minus beta 0. So because it's minus, so this one will also be minus beta 1 xi all squared. Is it clear now?
Yes, it is.
yes,
Thank you very much. So this is our, it's our normal function. This is the distribution function. This is the distribution function. So we are going to use the maximum, or the method of maximum likelihood to estimate beta 0 and beta 1. And that one is given by the product of the function. So it's the product of the function. We're going to have the product of our function. So our function is 2 sigma squared minus 1 over 2 e to the power sigma squared minus the mean, which is beta 0 minus beta 1 xi. Someone raised their hand, and as I've said last week, that when I'm on whiteboard, I cannot see the hands. So if you have something, please. You are recognized. All right, so let's progress. Now, the product of this constant is going to be, because it's like we discussed this on the first day, that the product of the constant is the constant to the power depending on the number of the last one here. So we are going to have to the power n over 2. E to the power, so the product of this, because there's I here, so we are going to sum this part to n. So we're summing this to n. So this one is the likelihood function. This one is the likelihood function. And then how do we then get the values that maximizes this likelihood function? We differentiate the likelihood function with respect to the parameters. So we'll differentiate with respect to beta 0, and then we solve for beta 0. We differentiate with respect to beta 1. We solve for beta 1. However, the values that maximizes the likelihood function are the same as the values that maximizes the log of the likelihood function. So if you solve the likelihood function, or you solve the log, the natural log of the likelihood function, so you're going to get the same values. So those are the values that maximizes the likelihood function. So instead of dealing with this, because it's complex, the best way is to find the log of the likelihood function and solve that, because the values that you get are the values that you would have obtained when you solved the log, I mean the likelihood function. Is it clear?
Yes,
Yeah.
sir.
Yes.
Thank you. So we take the natural logarithm of this. So we have log e of beta 0, beta 1. And this is going to be, so the log of the constant, we're going to have negative 1 over 2, the log of 2 pi sigma squared. And the log of this is going to be minus the exponential part will come down. So we'll have this minus beta 0 minus beta 1 xi squared. So let me go to the notes, because these things are there in the notes. There's no need for me to write them. So let me go back to the notes. Let me go back to the notes so that I can explain from that side. So we take the natural logarithm of the likelihood function, and we get this, and we get this. So you saw how to get to this point. And as I've indicated, that we want the values of beta 0 and beta 1 that maximizes the likelihood function. And we obtain those values by differentiating the likelihood function, or the log of the likelihood function, with respect to the parameters. So if we differentiate this with respect to beta 0, this part is a constant. So if we differentiate this part with respect to beta 0, this part is out, it's 0. Then you differentiate this with respect to the function, with respect to beta 0. So you start with the exponent. So it will be we differentiate the exponent, then we come and differentiate the inner function. So we are going to have, because there's minus 2 here, or minus 1 over 2, and there's this 2. So this 2 is going to cancel with this 2, and we'll be left with minus 1 over sigma squared. When we differentiate the inner function, we differentiate minus beta 1, we get 1. And that we get minus 1, sorry, because it's negative. So that negative 1 will cancel with this negative 1, and we'll be left with 1 over sigma multiplied by this part. So that's what we are having here. That's what we are having here. Then we go back and differentiate the log of the likelihood function with respect to beta 1. So the constant has nothing to do with beta 1, so this part is 0. Then we differentiate the exponential part, so the 2 will cancel with this 2. Then here we have minus beta 1 xi. Minus xi is a constant. So when we differentiate with respect to beta 1, we'll have negative xi. So that negative will also cancel with this negative. And we are left with xi multiplied by that function. That's why we are having this guy here. Is it clear?
Yeah, it's clear.
Yeah.
So from here, you know what to do. We equate the partial derivatives like we did with the least square. We equate the partial
sorry to
I'm listening.
disturb. Can you re-explain the last part?
The last part, which is this one of beta 1.
Yeah.
All right. So we differentiate the log of the likelihood function with respect to beta 1. So what is the partial derivative of this with respect to beta 1? So this is a constant. So the partial derivative of this is equal to 0 with respect to beta 1. And then now we get to this. What is the partial derivative of this with respect to beta 1? So you have the exponential part and then the inner function. So we start with this, you know, the laws of derivatives. So we differentiate this, which is going to be 2. So we take it down. It's going to cancel because we have 1 over 2 here. So this 2 is going to cancel with 1 over 2. Then we have negative sigma, and I mean negative 1 over sigma multiplied by this. But we have to differentiate the inner function as well. And when we differentiate this with respect to beta 1, when we differentiate this with respect to beta 1, we are left with minus xi. And that minus, because there's minus here, that minus will cancel with the minus, or it will give us positive. So now we have a positive 1 over sigma squared multiplied by this function with the xi, because this xi is the one that came out when we differentiated negative beta 1 xi. So we have that xi here, and then the negative cancelled with this negative, and we have this comrade here. So from there, we equate the partial derivatives to 0, and we replace the parameters by the estimators. We replace the parameters by the estimators. So that's what we did. If we equate this to 0, let me go to the board, the whiteboard, so that I can explain this part, even though it's there in the least square. But I feel like I have to highlight some of the things. So let me get the whiteboard. So the partial derivative with respect to beta 0 give us of the log of beta, okay, is the same. Give us 1 over sigma squared yi minus beta 0 minus beta 1 xi. So it gave us this. So if we equate this to 0, we're going to have, we're equating this to 0, and we replace the parameters by the estimators. So we'll have, and this does not help us with anything. So we can divide both sides by this term. Like we did with the least square, there was 2. We divided both sides by 2. So if we divide both sides by that term, we'll be left with which is equal to 0. And you know this, I think it's equation 1, is it equation 2(1) or something in the least square. So you know how to move from here. And then the other one we are going to have, because it's the same procedure. It's the same procedure. So on the other one, we have something like this. And this is equation 3. Is it 3a or 3b in the least square? So from here, is the same as what we had in the least square. So you can proceed like that. So I don't have to repeat what we did. I can just scroll to the least square and show you what we are having that side so that you can see what's going to happen. So from here, that's why it's equation 2D and 3D, is because they are here. They are here. So after equating to 0, we obtained this. And then from this, we have these ones. You saw how to get to this last week. And then from here is the matter of making beta 0 subject of the formula and beta 1 subject of the formula. And we did that last week. So I'm not going to repeat that part. I'm not going to repeat that part because we covered it last week. Is it clear? Is it clear?
Yes, yeah, it's clear.
Thank you very much. So now, please guys, mute your mic. Please mute your mic. So Maluleke, please mute your mic. Maluleke LB, please mute your mic. Thank you very much. Thank you very much. So from here you can proceed. From here you can proceed because you are just going to copy what we did here. You are just going to copy what we did here. So you have the remaining parts of that problem. So you can just go and copy them. With the maximum likelihood, I'm interested in estimating the variance, because after this it's estimating the value of sigma, which is the population variance. So with the maximum likelihood, we can estimate the variance, even though the one estimated from the likelihood is biased. But we have to estimate it and show that it is biased. Also show that this one is unbiased. So we have this one. So you don't know where this one is coming from. We didn't derive it. I just explained last week. So I want us to go and derive from the likelihood, or from the method of maximum likelihood, because we do have sigma here. We do have sigma, so we can derive from here. We can derive it from here. So the procedure is the same. We substitute the function from the likelihood function, and we have this, which is our likelihood function. Then again, the values that maximizes this is the same as the values that maximizes the log likelihood is the same values that maximizes the log likelihood. So we're going to take the natural logarithm of the likelihood function. And when we do that, we get this. When we do that, we get this. So from here, we have to differentiate with respect to sigma squared, because sigma squared is what we want. We want to estimate sigma squared, or we want the value of sigma squared that maximizes this. So let's go back to the board. So again, the procedure is the same until you get here. And then when you get here, you have to differentiate with respect to sigma squared. So that is the difference. Now, we are no longer looking for the betas, we are looking for sigma squared. So we're going to differentiate with respect to sigma squared. Sorry, I want to project the whiteboard. So we're going to differentiate with respect to sigma squared. And our log likelihood function, sigma squared, is 2 sigma squared minus n over 2 minus 1 over 2 sigma squared, or let me just write it like this as well so that it can be easy. I'm praying that you guys knows how to differentiate, because I don't want to teach that. It's maths. So please. This one, it's 1 over 2 sigma to the power minus 2. So I'm taking it from down there. Now it's like this, and then we have so this is the log of the likelihood function. So we're going to differentiate this with respect to sigma squared. So the log of the likelihood function. Sorry, there should be log here. I forgot something. There should be, because we have already taken the log. So this should be minus n over 2, the log of 2 sigma squared. Is it clear? Is it clear?
Yeah, it's clear, sir.
Thank you. I'm asking because I was accused of moving fast. So I want to make sure that I'm traveling with everyone. So if you are not understanding something, feel free. So from here we differentiate. So this is the constant, but because it's multiplied with a term which is having sigma squared, then it's not going to be 0. So we're going to have this constant.
So
That's why I
you're
said
differentiating the log of what?
Of 2 pi sigma squared. Remember, we're differentiating with respect to sigma squared. I expect you to say something, whether you are understanding or not. Can I move?
Yes.
Yes,
I can.
Thank you. So the derivative, when we differentiate, let me write here. You have been saying the derivative of ln x, it's 1 over x, because is this x in the denominator, then in the numerator is the derivative of x, and that the derivative of x is 1. That's why we have this. So that part is clear. So that's why I said I don't want to go back to math 1. The assumption is that you did math 1. So now when we differentiate this, we're going to have 2 pi sigma squared, and then the derivative of 2 pi sigma squared with respect to sigma squared it's equal to 2
Sir,
pi. Yes.
this network cut me out while I was asking. What did you say?
We are differentiating with respect to sigma squared. So as you can see here, there is a sigma squared. So this thing cannot be a constant. So we have to differentiate this also with respect. Remember when we were differentiating with respect to beta 0, this was a constant. So we said the partial derivative of this is 0. But in this case, this cannot be 0 because we're differentiating with respect to sigma squared. So we differentiated the log of 2 pi, and the log of 2 pi, the derivative of the log of 2 pi, it's equal to this guy here. Then we move on to the next term. Now, we have minus 1 over 2. The partial derivative of this with respect to sigma squared, this is minus 2. So we are going to have minus 2 sigma to the power minus 2, which is minus 4. So this is going to give us minus 4. So we have sigma to the power minus 4. Then this term, we leave it as it is because there's no sigma there. But because it is there multiplied with our sigma squared, then we leave it as it is. So this part is clear. So this negative 2 is going to cancel with this and we'll have a plus. And this 2 pi is going to cancel with this 2 pi. So we are going to have negative n over 2, 1 over sigma squared, plus, now I want to rewrite this as 1 over sigma to the power 4, summation of yi minus squared. After differentiating, we set the partial derivatives to 0, and we replace the parameters by the estimators.
Sir,
Yes.
can you repeat that part of the second part where I differentiated, because I'm a bit lost there.
What is it that you are not understanding? Maybe I can assist you like that. So if you can be
The
specific,
part
then
of the part of -4, where is it coming from?
we are
Oh, sir,
differentiating.
sir,
Yes.
please start that with -1 over 2 to the power -2, and then before sigma squared -4.
Come again. I'm not getting what you're saying. I should start where?
-1 over 2 to the power -2, then sigma minus 1 over 4.
Minus 1 over 2. This part.
Yes. No, on the second
Sir,
part there. Yeah, that part, sir. That part. Yeah. Explain that part.
Guys, please. Like now I'm hearing like the number of people who are, I cannot, please, one at a time, please, so that I can understand. Please, one at a time. Let's start with the first one. You said which part you don't understand?
The part where we got -4.
All right, let me explain that part. Then the next one will come. I will accommodate everyone. We are differentiating with respect to sigma squared. It's unlike when, please mute your mic, guys. It's unlike when you are differentiating with respect to, if you differentiate with respect to x, for example, you are differentiating x. It's x to the power 1. So you take 1 down and you say x 1 minus 1. Then that's why this is going to be 0. Then you are left with x 1 multiplied by x to the power 0, and you have 1. So what we are having here, I thought you guys did mathematics, you know how to differentiate. Now, we are differentiating sigma squared with respect to sigma squared. So it's squared and squared. So when we differentiate like we did with x, it's going to be 2. We take 2 down, sigma 2 minus 2, because this is 2. We are differentiating with respect to sigma squared. And this is going to give us 2 sigma to the power 0. And sigma to the power 0 is 1. So we'll be left with 2. That's why here, let me change a color. That's why here, when we differentiated this part, sigma 2 pi is a constant. So we are left with a constant, but the partial derivative of sigma squared gave us 1. That's why there's nothing here. It's because of this. We did this to that part. Then we go to which part now? We go to this part. We have minus 2. Minus 2 minus 2 will give us minus 4. Is it clear? And
Yes,
again,
sir.
I missed something here. I missed something. So when we differentiate these 2, there was supposed to be another 2 here. So that 2 will give will give birth to 4, because we'll have 2 multiplied by 2, and this is going to be 4. So this 2 was supposed to be up here, something like that. I think something is missing up there. So let me erase this, and then we start here, how to differentiate. There's something that I wanted to show you. Let's go back. So we are here. Let me take my pen, black pen. Now we are here. This is a constant. We leave this as it is. The partial derivative of a log, we have the part inside the log in the denominator. Then we differentiate this. And this is going to give us what? It's going to give us 4 pi, because we'll have 2 multiplied by that. We have this. We come to the second one, minus. This negative 2 is going down. And because there's negative, now we have plus. This 2 will cancel with this 2. Then we have sigma to the power. It's negative 2, negative 2. This will give us negative 4. And then we have this part. Is there anyone who did not understand this?
Sir,
Yes.
I have a question here. When we differentiate 2 pi sigma square, it was not supposed to be 4 pi sigma.
No, you are differentiating with respect to sigma squared. So it will be squared minus 2, and that will give you 0. And that 0 will, yes.
All right, thank you.
You are welcome. So that's what we are having there. Yes.
I don't understand where does this 4 pi comes from.
What is the partial derivative of, let me do it, write it here. What is the partial derivative of sigma squared with respect to sigma squared? What is the partial derivative of this? It's what?
1.
It's 2, sir.
It's 2.
Yeah.
Guys, I don't know how to, because I have to do this, and now it's more like I'm taking you back to math 1. I did not want to do that because of time. I assumed no, it's fine. I will explain it. I assumed that you guys know how to differentiate. The partial derivative of this,
It's
it's
minus
equal to
n
1
over 2 pi.
x.
It's minus n
equal
over
to
2 sigma squared.
this.
Sir,
Yes. Can I please explain to the person who asked the question, then he will come. The partial derivative of ln x with respect to x, you are saying this is equal to 1 over x. You are saying this is equal to 1 over x. And I've explained that it's equal to this because we are having x here. Then here we should have the derivative of x. And because this is x and this is x, remember x is to the power 1. So we take that exponential part down. We have x 1 minus 1. So this part end up giving you x to the power 0. And x to the power 0 is 1. That's why you end up with 1, because it's 1 multiplied by 1. So in our case, we have, let me erase this. Here we are going to have, let me do it like this, the ln of, so the partial derivative of this will give us sigma 2 sigma to the power 2 minus 2. And this is going to be 0 and this is 1. So we end up with 2 over sigma squared. Is that one clear?
Yes, sir.
So here there was 2 pi, and this is a constant. So that 2 pi, because it's a constant, will be here. So this 2 multiplied by 2 now will give us 4 pi. That's why now we're having this 4 pi. Are you answered? Are you answered? Let me just finish with this one. Are you answered?
Yes, sir.
Thank you. Now I'm recognizing the one with the hand up. I don't know, because I cannot see what's happening that side.
Sir,
Yes.
from where I got the information, sir, it is the partial of the log maximum likelihood function to sigma squared. It gives us minus n over 2 sigma squared 1 over 2 sigma to the power 4, the sum of yi minus the estimate at I.
Can we proceed with
Yes.
what we are doing here? Not with what is there. Let's proceed. So we have we have 4 here, because this is 2 and 2, so it's 4. So this 4 pi will cancel with this 4 pi. Now we have this plus 1 over this one. I can write like this: yi minus beta 0 beta 1 xi squared. So we equate this to 0 and replace the parameters by the estimate. So what are the parameters? We are going to replace sigma squared by s squared, which means this is going to be s to the power 4, and this is going to be beta 0 hat, and this is going to be beta 1 hat. So we are replacing the parameters by the estimate. So, and we equate that to 0. So we're going to have 1 over minus n divided by s squared plus 1 over s to the power 4 yi minus beta 0 minus beta 0 ahead, because even this one we are replacing xi all squared. Right? So this part is clear. we equate this to 0. So we can now take this thing to the right because we have equated this to 0. So we can have an expression on the right and also something on the left. So I'm going to take negative n over s squared to the right. So on the left, I will be left with on the left, I will be left with, or we will be left because we are together. If something does not work out here, you will say I have been alone. So I'm with you. So this is why this part is y I had. So I can write this part as minus y I had. I can write this part as minus y I had, which is equal to n over sigma, s squared. Is that part clear? I don't want to leave anyone behind. Is that part clear?
Sir,
Yes.
what happened to the squared?
No, it must be there. Thank you very much. So it must be here. Thank you very much. So this is squared. As you can see here, it's squared. Thank you for that. So I can multiply both sides by s to the power 4. I can multiply both sides by s to the power 4. So you know it's mathematics, it's allowed. So if I multiply both sides by s to the power 4, on the left, I will be left with minus yi had squared, which is equal to this side, s to the power 4 divided by s to the power 2, I will be left with s to the power 2. Is that one clear?
Yes.
So I divide both sides by by n. So if I divide both sides by n, our s squared is equal to ni minus had squared divided by n. And this is the estimator of the population variance from the maximum likelihood. And this estimator, as I've said when we're starting, it's biased. It is biased. So we are going to show that this is biased. It's not unbiased. And because it's not unbiased, we cannot use it. That's why we're using the one with where we're dividing by n minus 2. So showing that this is biased, it will that one will lead us to showing that the other one is unbiased. Then we will be killing two birds with one stone. So that's what we're going to do. We're going to show that this is biased, and then the other one it's unbiased. And you know from stage 2 that the expected value of s, where we are dividing by n, not n minus 1, it's biased. You know this from stage 2. But I'm going to cover that. There is someone, when I was proving this, saying from I don't know whether I was Googling or what, I have this and that. I hope at the end they're having what I'm having here. And please, when I'm doing this, don't say from the sources I'm getting this, because we are not yet done. If my final answer is not the same as their final answer, then you can say what you are having is different from what I'm having. But you cannot stop me while I'm busy working out on the problem and say what you are getting from the internet on that step is not the same. Obviously, it's not the same because I know what they did there, but I don't want to tell you because it's not my business. So what we have to do is to pay attention and see why we are not having the same. They did not treat this part. They separated this part, but you did not notice that because you are rushing to tell me that what I'm having is not the same as what is in the internet. They divided this into 2. They had the log of 2 pi to the power negative this, and minus the log of, they treated this sigma squared like this because it's allowed in mathematics. You know, in mathematics, the log of AB, is it the log of A minus the log of B? That's what they did to that. So please, when I'm working out on a problem, if you are ahead, you got something from internet, wait for me to finish so that you can say, but the final answer is not the same. The steps might not be the same. What matters is the final answer. Like I said, when we were starting that there are a number of ways of solving these things, and we're not going to look at which method did you use. What matters is are the steps correct? Because you can have the correct final answer, but with the wrong steps, because you can copy the final answer somewhere. So we check if what we are having is correct or not. So from here, from this part, I'm going to rewrite this I'm going to rewrite our S, and I'm not going to derive this because we did derive this last week to save time, because I can see time is not on our side. So what we are having, let me erase this. Okay, it's fine. This part in the numerator, it's nothing but the summation of EI squared. As you can see, this is the error. So it's the summation of EI squared. And we said this part is nothing but SSYY minus beta 1 at SSXY divided by N. Yes.
You forgot the squared.
Thank you. Thank you very much. Squared. Thank you very much. So this is what we are having. And you know that this part can also be written as, so don't memorize, guys. You have to understand these things, because like I said, you don't know how the question will be presented to you. You cannot set your own questions. So you have to know all these angles. And don't say you showed us this, you didn't show us that. Even in primary, they teach you 1 + 1, but they don't ask you 1 + 1 in the test. So you cannot say no, but you showed us this, you didn't get to that point. Even when we are doing a multiple of 2, we stop at 10. But now you know that 20 times 2 is 40. No one taught you up to 40. So please, what you did on Friday during the tutorials, claiming that no, we didn't cover this in class, obviously we are not going to cover it as it is. If we estimate the regression, and I don't start there to say estimate the regression, you know how to get the betas. So I don't have to ask you how to get the betas. You cannot expect me to ask you to estimate beta 0. You are saying you are going to write an assessment, and I get there and say estimate beta 0. So let's proceed. What I'm going to do again here, I'm going to replace this by this, because it's working on my advantage. When I'm having SSXY, it means I have a function of y, and that's y again in beta 1. So this thing now it's complex. But if I have it like this, beta 1 squared, I know that this is a constant. So I'm avoiding dealing with SSXY. Now I'm introducing a constant over n. So we have to find the expected value of S. That's what we are going to do. And to find the expected value of S, it means we must find the expected value, because this is a constant, we take it out. It means we have to find the expected value of SSY minus beta 1 hat squared SSXX. And this means we have to find the expected value. Let me write here. We have to find the expected value of SSYY minus, because this is a constant, or let me close this because the 1 over n covers everything. SSXX, the expected value of beta 1 hat squared. So that's what we are going to find. So I'm going to do this separately. I'm going to first find the expected value of beta 1 squared, and then I will come back and find the expected value of SSYY. And then I plug into this and see what we will get. Is that one clear? Is that one clear?
So what did you say?
Come again, sir.
Let me erase this. Our S squared, it's equal to 1 over n, let me write it like this, SSYY minus beta 1 hat squared SSXX. So I want the expected value of S. And because this is a constant, we leave it out. We have the expected value of this guy here. And now we can distribute the expected again. We're going to have the expected value of SSYY minus the expected, this must be squared, the expected value of beta 1 hat squared. Because this is a constant, we cannot find the expected of that, so we leave it like that, it's a constant. So I'm saying, I'm going to first find the expected value of this, I come back and find the expected value of this, then I plug them together, because I don't have a space where I can find them like simultaneous. Is it clear?
Yeah, it's
Yes.
Yes.
Thank you. Thank you. So now I'm going to find this. I'm erasing everything, but you know that I'm going to find the expected value of beta 1 squared. So I want the expected value of beta 1 hat squared. And I know, because we proved this last week, that the expected value of beta 1 is equal to beta 1. And the variance of beta 1 hat is equal to sigma squared over SSXX. We showed this last week. And I know from stage 2, I know from second level and also first level, that the variance of beta 1 is nothing but the expected value of beta 1 hat squared minus the expected value of beta 1 all squared. You know this from second level. So I know this value. I can substitute here SSXX, which is equal to, I don't know this, comrade, is what I'm looking for. And I know the expected value of this because it's here. It's beta 1, then I square. So I can make this subject of the formula. So if I do that, now I have the answer of the first part that I was looking for. Now I have the answer of the first part that I was looking. So this is going to the right. Now it's changing the sign. It's going to be plus beta 1 squared. So this part is covered. Is there anyone who does not understand that part? Is there anyone who does not understand that part?
Sir,
So, yes.
the variance of beta 1 hat is
Yes.
equal to the expected value of beta 1 hat squared, right? Minus
I don't
the
understand. I don't understand.
You see the second formula, the second line.
This, all right. I thought you were talking about this. Now I get you. Proceed.
The second line.
We are here, right?
Yes.
Yes.
After getting the expected value of beta 1 hat squared, there is the expected value of beta 1 hat all squared. But then on the third line, it's only beta 1. It's minus beta 1.
Yes, because the expected value of
no,
1 hat is equal to beta 1.
Oh,
yes.
I just.
This is an unbiased estimator. Yes. So we substituted by this.
Yeah.
Thank you. Thank you for that.
Thank you,
so
sir.
This part is clear. So please don't forget this part, because we are going to need it when we go back and substitute. Let's go back and look at the expected value of SSYY. So now I want the expected value of SSYY, and I'm going to write SSYY, which is yi squared minus n y bar squared, like this. So now I want the expected value of this. And now I can take this in again. It's going to be the expected value of yi squared minus n expected value of y bar squared. So again, I have two terms. I have to find the expected value of this and also the expected value of this and come back and plug in here. But this is easy. We know that the variance of yi is equal to expected value of yi squared minus the expected value of yi. Right? And we know that the variance of this is sigma squared, expected value of yi squared. And we know that the expected value of this is beta 0 plus beta 1 xi squared. So I can make this subject of the formula. And if I do that, squared will have sigma squared plus this part. Now I want to expand this. This is a and b. So a plus b squared is equal to a squared plus 2ab plus b squared. So I'm going to do that to this part. So this will give birth to beta 0 squared plus 2ab, which is beta 0, beta 1 xi plus b squared, which is beta 1 squared xi squared. Is that part clear?
Yes.
Yes.
Thank you very much. So now we know, we know the answer for this comrade here. We know the answer for this comrade. It's here. Don't forget it as well. If you are copying, then make sure that you have copied it. So don't forget it. Now I want to find the expected value of y bar squared. Now I want to find the expected value of this. So I'm going to erase, and then we find this. We come back and plug in. And remember, we're still going to plug in to the first one there. So don't mix these things. Now I'm erasing this. I'm erasing that. Now I want the expected value of y bar squared. You are recognized. Okay.
Sir,
And I know, yes.
can you please go back to the last what?
Next time, please raise your hand before I erase, because I have
Isn't it that
erased.
minus multiplies the whole thing?
Which minus? This one.
Yes, like
I
isn't
took,
it that
this.
that minus that
Listen,
yes, is it not
listen.
multiplying the whole thing?
Listen, I took this to the other side, so the sign changed. It's negative now. I want this to be subject of the formula, so I'm taking this one to the other side. So we're crossing the river Jordan. So we have plus.
Okay, now I get it.
Thank you. So now I want the expected value of this, and I can get this from the variance of y bar expected value of minus y bar. Right? So I know, okay, let me just write what is y bar so that you can know. Y bar is nothing but 1 over n summation of yi. So the expected value of this is the same as the expected value of this. And this will give us beta 1 plus beta 0 xi, like this. Then you distribute in the summation. This will give us n beta 0 plus, because of xi here, we'll have this, right? Then you multiply everything by 1 over n, you will have this plus, and this one divided by n will give us x bar. Is that one clear?
Yes.
Is that one clear? So the expected value of y bar here, we're going to substitute by this guy. By the way, that's a square here. This thing is all squared. So we're going to substitute here by this guy. Now, what is the variance of y bar? What is the variance of y bar? The variance of this is going to be 1 over n squared because it's a constant. The variance of yi. So the variance of yi is sigma. When we sum sigma n times, we'll have n sigma squared over n squared. And this will give us sigma squared over n. You know this is the variance of y bar. Is this one clear? You know this from second level. I was just trying to remind you. Are we together? Are we together? So please, guys, understand these things, because when we are doing them like this, it does not mean I'm going to ask you as they are, or we are going to ask you as they are. No, we are not going to do that. Please understand what's happening here. So the variance of y bar is sigma squared over n y bar squared. Sorry. This one is beta 0 plus beta 1 x bar. We showed that. So we make this subject of the formula. We have over n. We are taking this one to the other side, so this becomes positive. But again, this is a plus b squared. So a plus b squared is nothing but a squared plus 2ab plus 2ab plus b squared. So we have this again. Is this clear? So now I'm going to, let me write the other one so that you can see where these things are going to cancel each other. The other one is this one. And we obtained sigma squared plus beta. I said, don't forget, I believe that you are having it. And here we had what? We had what here, xi or summation of xi. What was that? Please remind me. Guys, are you still with me? Are you angry?
Yes.
Here we have summation of xi plus beta 1 squared summation of xi squared. We had something like that. And because let me do this. Please mute your mic. So we want the expected value of which is equal to the summation of the expected value of this. No, the summations were not there here. These summations were not here. It was only the x. We had xi here, and we had xi squared. The summations are going to come in from this. Now I recall. Yes.
Where
Minus
did
n.
n go?
Come again.
The last step.
Yes.
Where did n go there? Because it was sigma
Which
over
n?
n. What happened to n?
Which n?
Look at the step above.
Sorry?
Look at, I get the step above is
Sigma
sigma
squared
squared
over
over
n.
n. So the one below is
Sigma
now
squared.
sigma squared.
No.
What happened to that n?
These two are not
It's
the
not the
same.
same
These two are not the same. Remember, this one, the bottom one is for this part. We started with this, and the top part is for this. So now I want to substitute here. Remember, I said we're going to do this, and then we do that. We come back to this and plug in. So these two are not the same. That's why if you look at this, there's x bar. Here there's xi. Here there's x bar squared. Here there's xi squared. So these two are not the same. Please don't confuse them. Is it clear?
Yes, sir. Thank you.
Thank you, thank you. So now we are substituting because there's summation here and this part is going to come here. So let me do it here so that you can see what's going to happen. I can bring that summation here on the bottom one. So summation of this, because it's a constant, is going to be n multiplied by the constant. The summation of this, because it's a constant, it will be n multiplied by a constant. The summation of this, because there's xi, will have summation of xi here. And here we'll have summation of xi squared. So the first part is going to be n sigma squared plus n beta 0 hat plus 2 beta 0 beta 1 summation of xi plus beta 1 hat, beta 1 squared, sorry, summation of xi squared. So the summation is coming from here. Now, I bring in minus here. I'm going to, let me bring n without the minus. Let me just bring in n there. And then that n, this n will cancel with this. I will be left with sigma here. Here I will have n, and here I will have nx bar. Here I'm going to have n multiplied by x bar. Nx bar, it's equal to summation of xi. So it's going to replace this by summation of xi. Here, I'm going to have n x bar squared. Is it clear? Is it clear? So I'm taking this part now and substitute here. So I'm going to have sigma squared minus, sorry, plus n beta 0 squared plus 2 beta 0 beta 1. Because this now has changed because of nx bar, where summation of x bar, summation of xi plus beta 1 hat, beta 1 squared nx bar squared. Now, if you look at this, it's the same as this, and there's this negative, so these two will cancel out. If you look at this, it's the same as this, and because of this negative, it's going to cancel out, and we'll be left with n sigma squared minus sigma squared. This part, which is beta 1 squared summation of xi squared minus this part, which is beta 1 squared as well, and x bar squared. Is it clear? Let me erase this part here. Is that part clear? Is that part clear? So it means we're together. That's why you're not asking anything. It's fine. It's fine. Let's just move on. I erased sigma squared here by mistake. So what I'm going to do now, I take sigma squared here because it's a common factor. I will be left with n minus 1. So here I factored out sigma squared. And if you look at this, beta 1 squared, it's also a common factor. So I take out beta 1 squared. I will be left with xi squared minus nx bar squared. And if you look closely, this part, it's nothing but SSXX. So now I have sigma squared n minus 1 plus beta 1 squared SSXX. So this is what I'm having. This part, it's equal to the expected value of SSYY. Don't forget that. So now we have the expected value of SSYY and the expected value of beta 1 squared, beta 1 hat squared. Now we can go back to the original equation or original formula and substitute and see what we are going to get. So now I'm going back to the original formula where we started. So now I'm going where we started, which is s squared 1 over n the expected value of SSYY minus expected value of beta 1 hat squared SSXX. So now I have these two terms. I'm coming in here to substitute. This is 1 over n. This we just proved now that it's equal to sigma squared n minus 1 plus beta 1 squared SSXX. Now we have minus SSXX, which is this, into the expected value of this. And we said the expected value of that is equal to what? We said it's what? It's sigma squared over SSXX plus beta 1 squared. I remember someone was asking why the hat is no longer there. So we have 1 over n sigma squared n minus 1 plus beta 1 squared SSXX. So this will cancel with this and we'll have negative sigma squared. This multiplied by this is negative beta 1 hat squared SSXX. And this will cancel out with this. And we are left with sigma squared n minus 1 minus sigma squared. Now sigma squared is a common factor again. If we factor out, we are going to have sigma squared n minus 1 n minus 1 again. Let me erase and write it properly so that you can see. This is negative. So if we factor out sigma squared again, we'll be left with n minus 1, which is this, minus 1 from here. So minus 1. And this is n minus 2. So as you can see, I'm going to write this as n minus 2. I'm going to write this as n minus 2. Now we have n minus 2. We have n minus 2. And now we are done. We are left with what? 1 over n sigma squared multiplied by n minus 2, which is not equal to sigma squared. Therefore, S is unbiased. N is biased. So this S is biased. Is it clear?
Sir,
Yes.
Explain how do you factor the sigma squared?
All right, it's fine. I will do it here. I will do it. Let me use a different color. You have sigma squared n minus 1 minus sigma squared. So you take out sigma squared, you will be left with this, which is n minus 1. You can even put it inside the bracket. Here you took out sigma squared, you are left with minus 1. So you deal with the brackets first, and this will be n minus 1 minus 1. Minus 1 minus 1 is minus 2, and this will give you n minus 2. Are you answered?
Okay, I see it.
Thank you. So at the end of the day, we have expected value of s squared, which is equal to 1 over n. I can also put this n minus 2 here, sigma squared. We have this, and this is not equal to sigma. Therefore, this is biased. But if we take our s, which is equal to n over 2, the summation of yi minus yi hat, because this was going to be our constant, and we know that this is constant, we know that the expected value of this part here is what we just obtained. We know that the expected value of this part, it's nothing but n minus 2 sigma squared, and we have n minus 2 here. So this n minus 2 will cancel with this, and we are left with sigma. That's why this one is unbiased. I hope it's clear. That's why we are using this one, not the one where we are dividing by n over 1, because this one is biased. So instead of using this, we go with this one because it's unbiased. I hope it's clear. So again, don't memorize those steps. You must know how to get there. So when you get time, please go and try those things. Try to understand them. If you don't, please mute your mic.
Sir,
Please mute your mic. Yes.
sir, may you please go back to the board?
So guys, please go and understand this. Try to understand these things. Don't memorize them. Yes, I'm here. I'm on the board. You said I should go back to the board. Can you see it?
Yeah, I wanted to say something.
Okay, thank you.
Thank you.
All right, thank you. So please, guys, try to understand that. Try to understand that there's no manna that is going to come from heaven. You have to work for your things. You have to work for this. So there's nothing that is going to fall from heaven for you to pass. Never. And by the way, you're going to write test on campus. I want to believe that you have that information by now. So these things of copying from friends, it's things of the past. So you must be prepared. You must be prepared. So what we're showing now is that this is an unbiased estimator of sigma squared. This is an unbiased estimator of sigma squared. So you must know that. You must know that. We did this last week. We have these properties. I think we still have time. So we can look at 1, 2, and 5. Then we'll do 3 and we'll do 3 in the afternoon. Then we look at some real problem. I think we are almost done with proving. So let's just look at these proofs. The first one is that the sum of errors is equal to 0. So how do we do that? How do we show that? You can also see that the sum of errors is equal to 0 from here, by the way. Let me go back and show you. You see this part? Because this part, this is EI minus YI hat. And EI minus YI hat is equal to what? It's equal to the error. EI minus YI hat is equal to EI. So that is the error. So the sum of that is equal to 0. You can see it from here. So when we prove, we are taking it from here until we get to 0. So I'm going to the whiteboard to show this. I'm going to the whiteboard to show that. Let me share the whiteboard. Let me share the whiteboard. It won't even take time. It's not complicated. It's straightforward, but you have to know it. You have to know these things. So we want to show that the sum of the errors is equal to 0. What we know is that the errors, it's yi minus yi hat. And what is yi hat? Yi hat is beta 0 hat. Because of this negative, we'll have negative beta 1 hat xi. So we want to move from here until we get 0. There's beta 1 and beta 0 and beta 1. So we need to get rid of one of these two. And we know that this one is simple. We can just change this because this is equal to y bar minus beta 1 hat x bar. So we can replace this by this rate. And if we do that, we have this x bar minus yi minus y bar. So this now is going to be plus x bar minus beta 1 at x bar. I'm going to arrange this. So this is going to be one term, and this one is going to be one term. I'm going to take beta 1 as a common factor there. I'm going to take beta 1 as a common factor. So what I'm going to have is the summation. I cannot see what you are typing. So you have to, if you are talking to me, you have to use your mic. Now I'm starting from this side. So I will have minus beta 1 hat into xi minus x bar. So x bar now it's minus because I started from this side. I took minus beta 1 as a common factor. So when you bring in the summation, you'll have the summation of this guy minus this guy minus beta 1 hat, the summation of this guy. On our first day, we showed that this is equal to 0. And this one is also equal to 0. So we have 0 minus beta 1 hat multiplied by 0. And that gives us 0. Is it clear? Is it clear?
Yeah, it's clear, sir.
Thank you. Thank you very much. So this one, it's very simple. This one is very simple. Let me do number 5, because even number 5, it's simple. Number 5, it's saying the summation of yi hat over n, which is nothing but yi hat bar. They are saying this is equal to y bar, the actual y bar.
Can you please go back?
So,
Can you please go back to
please,
that one, the first one?
please stop me before I start something. When I say it's clear, please talk so that we can. You cannot leave me to go to the next one, then you say go back, and we won't finish. We won't finish. So please stop me while I'm still on the problem. I asked whether it's clear or not, and you did not speak up. Someone said yes, it's clear, and I moved. Like I said, I won't like write something and erase without asking you guys. So can I move?
Yes.
So this is what we want to show. So we have summation of yi hat over n. And this is, we know what is yi hat. So these ones are very simple. It's something that you are having. Then I'm going to replace this again by y bar minus beta 1 at x bar. So I'm going to replace that. And if I do that, I will have what? What is it that I'm going to have? Please assist.
yi
Y minus.
So I'm going to have y bar minus beta 1 at x bar plus beta 1 at xi, like that, over n, by the way. This part, all right, let me do it here. Now I distribute in the summation. We'll have the summation of y bar minus. I want to deal with this because I see there's a common factor here. So this will give me beta 1 at xi minus x bar. Can you see here? If I start with this term, take it here, then I have this. So if I factor out beta 1, I will be left with that. So when I bring in the summation, beta 1 is a constant, I will take it out. I have the summation of this. minus x bar. And this part is 0. Remember, we're dividing everything by n. This part is 0. So it will affect this. And we'll be left with summation of y bar. And summation of y bar is n y bar. And we're dividing by n. So n and n will cancel, and we'll be left with y bar. That's what we wanted to show. Is it clear? And this is not the only way of showing this, because someone will say what I'm having is not the same. So this is not the only way. I'm showing you the simplest way. There is the other ways of showing this, because again, you don't even have to use that this part is equal to 0. You can come up with something. So time is not on our side. I'm going to stop here,
Sir,
for now. Yes.
why are
Sir.
you always substituting for B0 instead of B1?
Because beta 1, it's having a lot of things. So if I substitute with that, it's going to take a lot of time. That's why I'm saying I have to look at like the simplest way of solving. That's why I said this is not the only way of solving. There are the other ways, but they are complicated, and I don't want to complicate things. I go with the simplest way of doing things to simplify my life. It's like we are going to Yan, but you want to use the R71. You know that you are going to take time at Makoba's Kloof. So you can just travel using the R81. It's simple like that. So there are number of routes to take you to Yan, but you have to choose the one that is best for you. So that's what I'm doing here. I'm taking the simplest or the best route.
Sir.
Are you answered? Yes.
I think you the last part is positive. That side is positive.
Which one?
Yeah.
Yeah.
From there. Yeah.
Thank you.
Yeah.
Thank you. Thank you. Thank you very much. Thank you very much. Thank you very much. Oh, it seems like, yes. I'm listening.
I heard you saying like we leave you to do another things, then we take you back. It's not like it's like this. Sometimes I ask a question, then I have network problems. When I come back, you have already proceeded, and someone said yes.
Yes,
We
I understand.
And
I
didn't
understand if.
And at that time,
if you had a network problem, you say it like that say, I had a network problem, please go back to this. It's easy. But if I ask, are we together? And you keep quiet, I move, you say go back. It's more like you are playing games.